All right, let's get started. So as I said, we are having guest lectures on hardness of posterior sampling and some smooth analysis. Advait Parulekar will be speaking. That's today's class and next class.
Right, yeah. So yeah, today we're going to do a quick recap of the posterior sampling that Sanjay talked about a couple of weeks ago, and then build towards a formal hardness result. One of the reasons I want to do this recap is just to do it a little bit more concretely in terms of the kinds of guarantees that we might hope for and then what we can try to get. And hopefully convince you that the hardness that we discussed, like the actual hardness result, even though it seems a little bit pathological and maybe like some anomaly that we can kind of ignore with, get around with some distributional assumptions or something like that, hopefully I can convince you that it is a little bit more fundamental than that. And what we really need to do is slightly modify the posterior sampling problem itself. And then on Tuesday, we'll do a little bit of machinery towards like a positive result on posterior sampling, like posterior sampling in quotes, because not exactly posterior sampling, and then talk about some kind of, talk about an actual result. These are some references. Okay, so quick recap. This is stuff that Sanjay already talked about on a couple Thursdays ago, but I'll just go over it one more time for notation, just to so that it's in your cache. We have an unknown x that we want to try to recover, and we're given noisy measurements of x. So we have this measurement operator a. So it's okay if I come here. No.
Because your bigger audience is online.
Right.
So if you show anything on the screen,
Yeah.
you realize nobody's following.
Okay, fine. I'll choose the.
If the table is too low, I can.
No. It's okay. It's okay.
Tell me when to stop.
Okay, this is fine. Okay, right. So basically, there's this this measurement operator that we have that we assume that we know, and given we don't actually get to see x, the thing that we want to recover, we see these noisy measurements y, and we want to try to recover the x. This is, I think, why it's called an inverse problem. It's one of the motivations for posterior sampling. And here's an example. Just to explain why this is like a Bayesian style problem, is suppose that this was my ground truth image, right? I have some like a picture of L cap, and I give you a measurement which is the whole image, but I black out some rectangle. So that's why, and maybe I put some noise in it. Now, one thing that you can try to do is this MLE estimate, which is just minimize the reconstruction error. And there's no real understanding of what, like any specific x's you want to recover. You just want to minimize this loss. Then really there's no difference between this reconstruction, and this reconstruction. I put I just leave it blank, or I reconstruct it properly, or I put a different cartoon in it, whatever. All of these things reconstruct well, right? Because you didn't know what was in that black region anyway, and it got masked out in the forward operator. The thing that we want to, what's missing here is any understanding of like a prior over the kinds of x's we want to recover. And we've been talking about these priors like for the whole semester, I think. And so we're going to modify this problem to be instead of like just returning like a single deterministic x, we'll return instead a distribution q star, right? And q star is going to simultaneously try to minimize your reconstruction error y minus ax squared, right? While also not straying too far in KL from your prior P. So this is the prior P that we know so much about. In particular, we assume we have these trained scores. So these are like the same scores, like the noisy scores for the prior that we've been talking about this whole, like the whole DDPM story, we had these trained scores. And we assume that we have those again here for the prior that we care about. And now besides this reconstruction error, we also have this KL penalty for straying too far from that prior. This is a couple of comments on what this loss is. So I just rewritten it over here. So first of all, of course, we're trying to minimize this reconstruction error. And then also we're trying to, the point of having this KL term is to maintain some kind of like semantic correctness to P. What I mean by this is, suppose like P was this red, these three modes, right? So these three, right? An example of a Q that works pretty well for this penalty is this one, right? This one on the left here. So some of the modes, maybe I don't need to preserve exactly what the weights are. I can actually even remove some of the modes, and this actually doesn't have a huge KL distance to P. The kind of thing that the KL distance does not like at all is making up a new mode, right? And this is the kind of like, if you think about like the motivation we had, this is like if I have certain types of images that I want you to reconstruct your measurement within this certain type of images. I don't want you to make up a new type of image and give me that. This is like the kind of thing that would happen if you made up like a fully new mode, and then it would have a large KL distance. So this is why this KL distance is there, but there isn't actually anything fundamental about this formulation. We just made it, so we took the inverse problem, which was really kind of a deterministic problem, and we made it into a, learning instead a distribution, and this is how we did it. One last thing is, instead of talking about y minus ax as like the reconstruction loss, generally we'll just talk about an arbitrary loss L. The one thing that we will assume later, actually this is not super important today, is that it's smooth and convex. But the important thing is that we know it completely. So we know this loss, we can backpropagate through it and whatever. These kinds of things we can do, and it's some nice thing. One of the benefits of this formulation, I think maybe why it became so popular, is because you can actually characterize the best distribution Q, right? Q star as just this. Like, so this was our prior, and then this is like a tilting or something like that from the reconstruction error. And the Q star that you get by minimizing that objective that we had is actually just this. I think Sanjay talked about this. Okay. Yes.
Is it a single measurement, or is it many measurements with many different images?
No, okay.
You're having a per image.
It's a per image thing. Or it's a per measurement thing. So you have this algorithm, posterior sampling algorithm, whatever. Somebody will give you a y and ask you to give the x that corresponds to it. So we're not going to be doing any kind of training or anything like that associated with a specific y. The y is given kind of at inference.
Yeah, but
Yeah.
given one y, not like 15 different y's from 15 different things, and you have to construct 15 different images. So there's like a batch version of this, where L is a sum over. So the reason I ask is that the problem you want to solve is to get a single L. But the problem you're solving is to make a distribution over all x.
Yes.
And then just sampling from a point.
Yes.
Right? It would make somehow more sense if you made a distribution and sampled it 100 times.
Not necessarily, because you're formulating as finding a distribution, but you're never actually learning the distribution. You're building a sampler which will sample from this distribution. If you think about DDPM, there is no Q. It is just a fictitious Q from which you're finally just drawing one sample. So, you see what I mean? Yeah.
Okay. Yeah.
Okay, so the reason we call this posterior sampling is because the posterior is the product of the likelihood and the prior. We had this prior, and we can think of this reward or loss function, whatever model that we had, as being like a log likelihood, and then this fits exactly into this Bayesian framework of I had a prior, now I have a posterior. I wanted to say one last thing about like the formulation of the problem itself, which is like the at least for now superficial, but I think more deep connection between like the composite optimization problem and the composite sampling problem that we have now formulated this as. So specifically, I think we've seen this kind of thing before, like this kind of duality between like the optimization worlds and the sampling worlds, where when you want to maximize log p, this is similar to sampling from p, right? And the algorithms look very similar as well. So this is gradient flow, right? Or maybe there should be a negative sign. Oh, right, it's a maximization. So this is gradient flow, and then Langevin is basically the same thing. You just put some noise in, and really what that noise is doing is kind of like an entropy regularizer, but the algorithms look very similar, and they also have some similar properties. The thing that we're trying to do now is we have this PE to the negative LY, right? The posterior from before. We know how to sample from just this part of it, right? This is like the DDPM type of thing that we know how to do. And we also know how to sample from just that part of it because I told you like LY is nice enough, it's convex or something like that. You can just run, maybe if it's strongly convex, you can quickly get a sample from it using Langevin dynamics. Now, what we want to do is do both of them at the same time, right? We want to sample from like the composite problem. And if you think about like this is on the right, we've got the sampling problem. The optimization problem is basically maximizing this negative Ly plus log p. And you might wonder if there's something that you can borrow from like the optimization world of sampling from this like composite, of optimizing this composite problem towards just the sampling. And this is actually related to split Gibbs. Sanjay talked about it. We're going to talk about it again really quickly. But I just wanted to say that these are kind of three ways of looking at the same thing. I haven't said anything deep at all. It's just reformulating, just putting different words to the same thing. Okay, so two algorithms really quickly that don't work really like for efficient posterior sampling. Okay, so we did talk about these already. I'm just going to go over them again and explicitly point out where they don't, why they don't work in polynomial time. So the first is split Gibbs. This is from reference 1 on the first page. Actually, it's from many references. This particular reference is an instantiation of split Gibbs sampling.
Yeah, if you go back, if you want the references, more references, go back to lecture number note 16.
Seven.
It gives a whole bunch of references.
Right. So again, coming back to the sampling, the optimization thing, we have this. We saw that the sampling from the posterior was similar to this optimization problem, right? Where I have this loss Ly of x, like that's the reconstruction thing, and then I have a log p of x, which we're going to think of as now a regularizer, right? If so generally, if p has an efficient prox operator, right, and L is smooth and convex, I think you can run what's called the proximal gradient method and quickly optimize this. Here, the prox operator is this, right? So what it searches for is a point that's close to the point that you evaluated at, which has a small value of f, right? So this is, maybe you've seen this before in like an optimization class. This is what the method looks like. You take a gradient step, right, for f, and then you use the prox operator. You can think of the prox operator as a projection, and this is kind of like a projected gradient descent, but it's for the setting where there isn't really a strong notion of what a projection onto f means. We'll talk about that connection more in a second, but this is the proximal gradient method, and it has like basically you can sample efficiently. The thing that you need when you run the proximal gradient method is an efficient way to compute. Oh, this is missing a p or something like that here. Whatever. So the thing that you need here is, we've really replaced this. It's missing a p or a log p. I'll just say p.
Okay, you might answer this, but this is like for just optimization of that.
Yeah, this is just for optimization.
Like, but it's like the back, I guess the backs from posterior. What is this?
Yeah, probably. But this is just the optimization thing. We're going to convert this into a sampling algorithm in a second.
You're defining maximum probability of x given measure.
Yeah. Right. So, but this is not a sampling algorithm. This is just the optimization algorithm. And right, this is pretty well known. We're going to replace now the proximal operator prox with a proximal sampler. So, see here we have this argmin of this. We're going to put that in the exponent and sample from that, and that's the proximal sampler. So it puts a lot of mass on places where this the prox operator has a low argument, and it's basically the sampling analog of the prox operator. And so it turns out, and we've discussed this, that this prox operator can be sampled from prox sampler can be sampled from efficiently using DDPM. I'm going to black box this. There's a reason for that. Sanjay already talked about it, so whatever. For the sampling problem, we know how to do this part efficiently because of the scores that we've trained, like DDPM. Yes?
The algorithm is, what is f? I'm descending on the likelihood or the...
I think that's a loss, right? That's the measurement consistency.
Yes.
You're saying that the prox corresponds to prior consistency.
Yes, the prox is for the prior, so that's the log p.
So what's the difference between L, F, and log P?
So F is like
This
L.
is conceptual at this point, right? You're not actually running this algorithm, or you are?
Well, we will in a second. But right now I'm just trying to motivate what split Gibbs does.
So sorry, I still don't know what F is.
F is a loss.
Is F equal F of? No, F is in Z and
It's
L
not
Y is in
by
X,
X
so I'm a little lost.
Oh, okay. Yeah, sorry. This F. Okay, so this F is just for the definition of the prox operator. It is the P. It is actually log P. This F here is the loss. My bad.
Ly. So this
Yes,
is like-
Ly. So I take a gradient step for Ly, and then I do the prox for P. P is my regularizer. Yeah, sorry. There's I have used F for everything here, but it shouldn't be.
It's fine, it's conceptual.
Okay. So
And is there a reason you do gradient on one and prox the other versus?
yeah, depending on what you have an efficient prox for. So this one should be for P.
I
P,
guess if you think, or I guess normally you think P is like some simple, like a
and
Gaussian.
then this one.
It's like a regularizer kind of.
Okay.
Yeah, wouldn't it be easier to do the prox for Ly and then take the gradient speed?
No, because we don't have either of those.
But we have the score.
Right, the score gets you the prox for P. We have the score for P. P is the prior.
Yes.
This DDPM
Yes.
gets you a prox operator for log P,
I see. Okay.
right? This is magic. I don't know how that happened. It just so happens that DDPM gets you this prox operator. And Ly,
Actually discussed this in detail in lecture 16.
Yeah.
Remember, they're just seeing that it's just noise, just reinterpreting that. Yeah.
right. So the reason we split it this way is because we do have a prox operator for P, and L, because we say it is, L is smooth and convex, and in this exact setting, proximal gradient method works pretty well for the optimization problem. And so now, does it also work for the sampling problem? So this is what split Gibbs tries to do, where you make a couple of modifications to end up here. Oh no.
Is this a standard interpretation of split Gibbs or something that you tell us? Like, this is your view, or is it, and when people say it's split Gibbs can be viewed as this, or is this your kind of conceptual contribution to this?
I think I don't know if it's ever been written out. I think it. I made this up, but it's correct. So maybe somebody, it's because I think it's true. Maybe somebody else is. No, I think okay. So this was something we were working on. Right.
I just made it a pure sampling problem. Didn't we assume nobody knows what a prox is, because I don't know what a prox is.
Right. Yeah. So this is my interpretation, and I think it's just it's nice to motivate it this way because there's a lot of similarities between optimization and sampling algorithms, and I think this is just another in a long line of similarities. So I don't think the original split Gibbs papers talk about it this way, but actually no. I think this. Okay, maybe I don't know. Okay, right. So a couple of modifications later, minor modifications. I don't want to spend too much time on this. So we get to the split Gibbs algorithm, which is essentially just an alternating set of prox operators. The first one for Ly, and the second one for P. And the P one we know how to implement because of DDPM, and the L one we know how to implement because L is nice enough that we can do anything with it, kind of.
The proxies with you regularize to the last data rate? Is that?
Yes. So you get xt prime from like the prox on the L term, and then you put that into the prox on the next. You just keep. Okay, I'll show you what this. Okay, prox you can think of as a projection, right? Like just kind of take my word for that. It's prox is like the version of projection that happens when you don't have a set that you're trying to project onto, but like a function that you're trying to get closer to or something like that. And then here's like an illustration of what this algorithm does, right? This picture is what I wanted to show, because of which we did this whole split Gibbs thing. Is imagine if this blue line was the set of valid images was just a line, this blue line, and the set of points that agreed with your measurements are this purple line here, right? So this is just y equals ax. Let's say a is linear. So this is y equals ax. A is some low-rank linear matrix. And so the points that are likely under the measurements are like this purple shaded region, and the blue is just the set of images you have. Then what the split Gibbs does is it alternately projects onto the measurements and then the images. Yeah, right. So you start here, just arbitrary whatever some sample, and then you project onto the set of things that are consistent with your measurements. So this would be like if I give you an in-painting problem, you make sure that whatever region you did see in the measurements, you just put that on there, and you keep whatever, like that little box will be some arbitrary thing from before, but the outside will have like the actual image. And then you project that onto the set of images. So now you do like a DDPM to make that look like an image, right? And now, of course, the measurements are messed up again because now it looks like an image. And so you project that back onto the set of measurements, and you project that back onto.
Yeah, I'm not saying that has that form. I mean, I know how to do a DDPM when I'm doing deep blurring at every step, but do I know how to?
No,
Give it what
right. No, you're right. So DDPM has will do the right thing if the iterate that you start from is actually the appropriately noised, appropriately noised point. But you can always run it from anywhere. Like you can run the algorithm.
plug it into fun.
Yeah. Yeah, assuming that your score functions are like well trained. Right. They're just trained for denoising arbitrary x's though, right? They're trained for denoising just in general from like what they're trained to do is give you the probability distribution from the posterior of clean images conditioned on the noised version of those images being the thing that you are just seeing right now. So you can always make this, assuming this score function is trained properly, you can always make this this sampler of p of like x0 given whatever xt you care about, right? Now this won't look like an image unless you start with a good point, but you can always do it.
X0 is pure, right? And now I'm thinking of A as being like in-painting.
Mhm.
So there's some part image blocked out, as you said, the scene part is put in, and then now I'm going to start doing DDPM.
Mhm.
I need to start with some T.
Yes, that T, it's,
Zero?
that's a, no, it's actually a very, you need to specify that. This is actually what we're going to get to. It's some eta for now, some T, you make it up 0.5 something. You need to specify one to run this algorithm. You're right. So you start with like 0.5 or something, and then you say, I'm going to pretend like this like specific point is like the 0.5 noised version of an actual point.
So to add to that, in fact, we derived exactly one correct T. And this was if you don't go through this prox thinking, in split Gibbs, it tells you what that T must be. We can specify what the right T is at each point.
Right.
What
So,
is the first? Or maybe it's not in there, but there's a way to figure it out.
for this algorithm right now, T is something that the amount of denoising that you do is something that you're going to make up at the start of the algorithm. Basically, the convergence rate will depend on that T, and also the distribution you end up sampling from. So if you set T to be really small, you'll get very accurate. You'll get a very close distribution to the right one, but it'll take you a long time in general. And if you so there's a trade-off, and you just specify it ahead of time. So anyway, if everything is linear, like I've said here, then you get this very quick. You quickly go down to here and see this middle point right here. That's the point that's good under both the prior and the measurement. That's like the thing that you'd like to recover. And so this is all nice. The problem is like if your picture looked more like this, right? You can get stuck. Like you go here, you project onto measurements, images, and then you go like that, and then you'd end up like just bouncing back and forth over here. And this is what you wanted, and you'll never make that happen. Like it'll take, well, it will happen eventually because there's some randomness in the sampling, but it will take a really long time. And I spent actually a lot of time trying to figure out anything about, can you say anything more about this rate? And I don't think so. So anyway, so Sujay, to come back to your point, there's an eta that you pick, and you run this algorithm with that eta. And then for that, whatever choice of eta that you end up with, the limiting distribution of this pair of iterates that you have, like the one that came right after the projection onto the images, and the one that came right after the projection onto the onto the measurements, the law of those iterates will converge to this will end up with this density here. And so the point is that the projection onto the images and the projection onto the measurements are allowed to be decoupled because you put in, if I had set eta to be 0, basically this would say that you cannot have them be separate. But if you set eta to be larger, you're kind of allowing some leeway where you're decoupling these two problems a little bit, where the images, you're allowed to solve the image problem kind of separately and the measurement problem kind of separately, and you end up sampling from this Q eta, right? Now, there's a problem with this, which is that imagine you had this kind of instance where these are my set of images, right? They're these like vertical pink lines, and then the measurement was this blue thing on the bottom. Then the actual posterior, right, is maybe supported entirely over here where they intersect. So there's no intersection in the other 3 bars. But what happens is Q eta, because it allows the x and x prime to be decoupled by around eta, it actually allows you to place some mass for x here and some mass for x prime over here, and like this. So if you look at the marginal on x, which is maybe what you'll do eventually, it will actually have some weight here, but then it'll also have some mass, some density out, corresponding to these other modes, which is wrong. And the problem is that even for small values of eta, you don't know, like, what value of eta should you pick, right, to make this, to make these things go away. First of all, you don't know, and secondly, even if you like the jump from, like in this case, eta to eta over 2 involves moving all of this mass, like whatever. You have like, you have these things over here up until a pretty small value of eta. This one, you thought that was right, but then for a slightly smaller value of eta, some completely different thing is right. So choosing the eta correctly is actually pretty important. And we don't even know for any specific value of eta how long it would take for this to converge. So there's 2 levels of problems with this algorithm. For any eta, how long does it take to converge to Q eta? And then also, what is the eta at which you're effectively solving the posterior sample problem that you wanted to solve? So both of these things we don't know. And honestly, I just don't know I don't know how to fix this analysis to get this like a end-to-end guarantee through it all. The papers that do talk about this just say asymptotically, what we'll do is we'll do like the inner loop for a fixed eta for a really long time. Eventually it will converge. And then we will slowly reduce the value of eta. And again, run it for a really long time. And again, keep doing that. And then we don't know how long this takes, but it will converge, whatever, in the limit, something like that. OK, so this was one attempt. It didn't quite work. Another attempt is using this Monte Carlo importance weighting estimator of this posterior score directly. So this was the thing that we wanted. Once we have this, we can just run DDPM. So why not just try to compute it from samples? We saw this identity in the previous class, and you can implement both of these expected values using samples, right? And this is basically an importance weighted estimator. The number of samples it takes, this is a paper this is a paper that talks about if I want to compute this expected value under one distribution and I have samples from a different distribution, how many samples would it take for me to compute this? And it's a little bit better, I think, than the rejection sampling bound, which is just the ratio of the densities. But over here, there's like a KL. So it's the KL of the distribution that you want to compute the expected value with respect to, and the distribution that you can compute samples from, right? So e to that KL gets you the number of samples that you would need for these estimators to converge, right? The problem is that this quantity, first of all, is weird because of these xt's. I don't know how to bound it at all. But even for like the one value of t for which we can get some handle on this, right? When t is like infinity, or when t is like super noise, xt and x0 are basically independent, and you can make this reduction, right, of pt of dot given xt and y is now just, you forget the xt, it's just p of dot given y and p of dot here. So it's just the KL distance between the actual posterior and the actual prior, right? So this is at least even the very first score estimation, right, at the most noise, will require you to compute an expected value from this, given samples from this. And there's a calculation here. I don't know if I should go into it, but eventually, what you'll see is that the number of samples that you need depends on this, right? The integral of p of x times e to the negative L of x, right? This quantity can be very small. It can be very small, for example, here, right? So if the points that my prior likes are these ones, and the points that my likelihood likes are these ones, right? The integral was the product of these, right? It's going to be very small, and it has this is basically the same problem that we had with rejection sampling, which was we were kind of just hoping that when we sample from the prior, we will eventually, after some time, we will just get the thing that we wanted, and then we can do this rejection sampling thing. This is a little bit, I think, slightly more sophisticated way of saying really the same thing, which is that I want to sample these guys here, right? And it's just going to take me a really long time to do it because I only know how to sample IID from P of X. This is like the only algorithmic tool that I have. And so far, these are two kind of natural ways to try to solve this problem, and they both are could be actually arbitrarily bad in runtime, I think. So what gives is that there's a hardness result, right? I don't know if there's like a good 30 or whatever 35-minute version of this. So I'm going to try to talk about this as correctly as possible, but I'm not going to be able to talk about it like fully correctly. There's parts of it that I'm just going to sweep under the rug because I think there are details that are not important. So for example, I'll tell you what I'm sweeping under the rug.
So where is this one?
Oh, this is the paper out of Eric's group. Okay, this is the diffusion posterior sampling is computationally intractable by Gupta et al. Out of UT actually. So okay, so this hardness result, what it says is that there is a prior p, right, that we can sample from in polynomial time. This is actually very important. This is what most of the work in the paper, I think, goes into showing that whatever prior they construct is something you can sample from in polynomial time. And a quadratic L. So forget about like any complicated measurement model. They literally have actually the instance that they have is an in-painting problem. So it's a simple quadratic L such that the posterior p e to the negative L cannot be sampled from in polynomial time under a standard cryptographic hardness assumption. So I haven't actually even said what sampled from in polynomial time means. What they have actually, the reason I don't say is because they have a different notion of distance. It's kind of like a TV distance, but not really. It's not a KL distance. It's something else, and I don't want to talk about what it is. But basically what they're saying is you cannot sample from the posterior efficiently. Okay. The cryptographic hardness assumption is also something I'm not going to get into. It involves the existence of a one-way function. So there's this thing called a one-way function, and they're saying that it does exist, and I think most people believe that it does exist. We'll talk about what it is in a second. Actually, we're going to talk about it right now. So you take a one-way function. So basically, I'm going to just explain what the instance is and roughly why it satisfies with the thing that they want. Okay. So the instance is you take some one-way function f. Now, a one-way function is something that you can compute forward but not backward, right? And the reason this fits very nicely into the posterior sampling problem is because remember it was like an inverse problem to begin with. So it would be a thing that would be hard to do is if you can compute the forward, but you can't compute if you had a function such that you could go forward, but you cannot invert it, it fits well into this like inverse problem framework that we have. But we'll talk about that in a second. So
can you define exactly what this one-way function is?
No, because so the one-way function actually takes in arbitrary length. The length of the input to the one-way function is unconstrained. For us, it is a function from RD to RD. This is actually not correct, but for us, let's just pretend like it is. It is a function from RD to RD such that f of x can be computed in polynomial time. So for any x, I can compute the value of f of x quickly. But for a y, right, the output of the function,
For all y or they exist or what? That's what I'm a little confused.
I believe it's for all.
I think it's for
Definition, I think, is for all.
Yeah.
we're not thinking, maybe in this scenario, we're not thinking of f as being some function with some kind of smoothness or regularity. Usually isn't like one-way function, something on like the 2 to the n or something like that.
Yeah. No. So right, I don't know if there are sufficiently nice one-way functions.
So you're saying for A, and let me pick any value of Y, it's going to be hard to find the value
No,
of X.
definitely not, because you
That
just start
doesn't
with
make
X, you plug it in, you get Y, and you know.
Yeah, I just reversed that. So I can.
No, but how would you?
But that's why I know the X.
No, but the input is a value of Y, right? You cannot. I'm not saying that you can't tell me what the input
No,
is.
but that there exists a Y. That's not for all Y. Because I will give you a Y for which I can do it easily. I will first choose an X, as you said, find f of X, that's my Y. For that Y, I can get back the X.
I think that will fall under the technical definition of why you, like, how it's defined, like.
No, there needs to be then some process for sampling f or something like that, because I can just write it down somewhere. And for all.
No, you can't. Okay, this I did look up. You can't write it down because that would enumerating everything would take too long.
I'm gonna enumerate some.
But the input is not one of the things that you wanted, right? The input is something that I will give you.
That's why I'm asking, is it for all Y or there exists a Y?
Okay, I don't know.
That's
Yeah, it must be there is some existence, because otherwise I can take all known one-way functions and just publish a list on my website of 10 solutions for each one, and then they're no longer one-way functions.
Okay, all right, fine. There's. I don't. So the problem is there exists a Y might be too weak for this.
And there's a bunch of, we're quibbling. I think clearly there's a bunch of Ys that we couldn't do this for, so let's say that.
Right, it's a function such that if I give you a Y, you can't invert it.
Yeah.
Okay. Because anyway, this is not the definition of a one-way function. This is a simplification anyway. The actual definition, I think, is unnecessarily complicated. Okay, we're going to, I think I'm going to spend literally the next 15 minutes just talking about this instance. It's a little bit complicated. Okay, so the prior P, this is what we're going to try to construct now, is a uniform mixture over a bunch of G sub S, right? Where S's are d-bit strings. Okay, so for every d-bit, so first of all, P is over R to the 2D, right? Our one-way function was from R to the D to R to the D, okay? So for any specific bit string, right, S, we're going to define a G sub S as below. First of all, a couple of definitions. This comb function is just a bunch of Dirac delta functions. So there's one, it's spaced out by epsilon. This epsilon parameterizes how far the individual combs are. And so this is comb epsilon of X. And let's just like this gamma sub sigma is a sigma squared variance Gaussian. This is pretty standard.
What is G? Can we go back to the basic definition?
No, G I haven't. GS I haven't defined yet. I'll get to on the next page. These are some auxiliary like right. So we're going to get to G sub S in a second. Before that, one more thing is P or whatever this is. Is this a psi? Sorry. So psi B of X, right? B is either plus or minus 1, is a discretized Gaussian, but the discretization is shifted depending on what the value of B is. So when B is -1, psi is these green ones, right? So it's shifted off center, right? But then discretized just the way that you'd expect. The spacing is again epsilon. And then when B is 1, you have the unshifted Gaussian, so it's kind of centered. So you have these two comb Gaussian things, and they're shifted a little bit. Now we can talk about what G sub S is. So the marginal on the first D coordinates, right, is just a standard Gaussian centered at R of S sub I. So for the R is an arbitrary scalar. So this is just some, not arbitrary, this is a scalar parameter. It's just some parameter that they will set appropriately. But basically, the first D coordinates are a standard Gaussian where the bias in the Gaussian depends on on S. So remember, we're talking about G sub S, right?
S is a D bit,
S is, yeah, so S is a specific D bit binary sequence right now.
and what is S sub I? Is the ith bit?
Ith bit in that D bit.
So it's 0 or 1. S sub I is just 0 or 1.
Yeah, yeah, 0 or 1. Actually, maybe -1 or 1. Okay. Yeah, but it's binary. Okay, and then f is our one-way function. The second d bits, right, are sampled in this way. You take this combed Gaussian, and if the ith bit of the one-way function is a 1, then you don't shift it. And if it is a -1, then you do shift it, right? So here's a picture. Okay, and then the full prior is just a uniform mixture over all S. Here's a picture of it. Okay. Okay. For a specific value of G sub S, suppose S, okay, S is not 0, 1 to D, it's -1, 1 to D in this picture now. But okay, suppose S is -1, 1. Remember, for every value of S, there's one G sub S, and then the full prior is a uniform mixture over all of these G sub S's. So for this specific G sub S, right, S0 is -1, S1 is 1, right? So this is S0, this is S1. And because it is like that, we have this Gaussian, the first bit of G sub S, the first coordinate of G sub S, the marginal looks like this. The second coordinate G sub S, the marginal looks like that. And then the third and fourth coordinates are the ones that encode the function value. And they are either, because f of S sub 0 is 1, this is like the unshifted comb Gaussian. And because f of S sub 1 is -1, the fourth coordinate is the other shifted Gaussian. This is, I mean, so obviously you look at this and you think this is like a very pathological.
Then lost.
Okay. So this is G sub S for S equals -1, 1. Okay, so this whole thing is the distribution G sub -1, 1. This is one component in the full prior, which is a uniform mixture over all such G's for every d-bit string. And this is for d equals 2 specifically, just for illustration.
That's what I mean. You have 4 distributions there. So what do you mean?
Those are the marginals on each of the coordinates.
Oh.
And the final distribution is a product. So the final G sub S is a product over these. And then the final P is a uniform mixture over all those G sub S's. Okay, like whatever, it is what it is. Is this, okay, just as a sanity check, what do you, does anyone know what the marginal on the first D coordinates of P is?
It'll just be like mixture of uniform Gaussian, the master.
All right, thank God. Okay, yes. So the mixture, so on the first D coordinates alone, G sub S, remember, is a Gaussian centered at 1. For every value of S, G sub S is a Gaussian at that point on the hypercube. And then you've got a mixture over everything. So you get like all of the points on the hypercube. And then the second D coordinates are some like weird comb thing. Right. But this is the instance. And so what ends up happening is that each G sub S, the distribution encodes this S comma f of S, right? So the first D bits encode like some D bit string S. And then the second D bits encode in this weird shifting way the value of f of S. And so if you see, basically the problem that they set up is that you observe the last D bit. So it's like an in-painting problem, right? So the first D bits are masked. You observe the last D bits. And this is enough to get you actually what the value of f of S is, right? But now the problem is, because this is a one-way function, you can't invert this to get the actual S. And in order to sample from the posterior, you have to have done that, right? Like a sample from the posterior will get the first D bits correct as well. And so because you can't invert this one-way function, you must not have been able to do this posterior sampling problem. Okay.
Why do you have to put the comb thing for the second D bit? Why can't you just do the hypercube thing?
That's a good question. So the reason for it is that, so the reason this works is that at low noise, okay, actually, let me answer that in like a few minutes. Let's talk about why this works, or some properties of this prior, right? First of all, the first d bits noise very nicely. They're just Gaussians. They noise in the way that Gaussians do. The second d bits do this interesting thing where at moderately high noise levels, they quickly wipe out any distinction in the phase, right? So here's a picture of that happening. I have this, this is one of the shifts, right? This is like psi of 1 or something. And then as I noise it, right, I quickly just get a Gaussian. Psi of -1 also quickly just becomes the same Gaussian. And so what happens is when you do noise the distribution, right, very quickly the last d bits no longer store any information about what f of s was. So if you want f of s for that specific g, you need to be at a very low noise level to where these combs are not yet mixed together. Now, whereas, right, and so at really low noise levels, we're in the setting where the combs are very distinct. So the second d coordinates do encode exactly what the value of f is, and the first d coordinates are all very distinct because they're on distinct points on the hypercube. And so if you compute the score at any value, right, the score kind of decomposes into components that come from a specific. For every value of x, there's a very specific posterior. Like there's one specific place where it came from. And this is because these distributions are so disjoint when they're at very low noise levels. Now, a different thing happens at high noise levels, right? At high noise levels, P is basically the entire distribution P is just a product distribution. Like it's a very simple, basically the first d coordinates is just uniform on the hypercube. The last d coordinates are all just the same Gaussian. And so in both of these cases, you can show, so the reason, so this is the answer to your question. The reason they have this more complicated setting is that they wanted to show that you can sample from this prior in polynomial time. In order to do that, they had to show that you can actually learn these scores for this prior quickly, and because in both in the two extreme cases, right, with very low noise, you have like very disjoint distributions, like very disjoint mixtures, and in very high noise, you have a product distribution. You can show that you can learn the scores efficiently. What happens when you try to encode, because another thing you could have done is what you said, I think what you were saying is you encode the first d bits, the S encodes the first d bits as a point on the hypercube, and then you just do the same thing with f of s. Yes. Right? You just encode that on the hypercube. What happens, this is, I'm quoting my brother, I didn't actually work this out. What happens in that case is that in order to compute the score at an intermediate noise level, the posterior of the, so the posterior, by posterior I don't mean from like a posterior sampling perspective. I mean like the distribution P of dot given xt, right? Just the like the DDPM posterior. This involves a mixture over several different values of s. Okay. Right, and then it takes a lot of time to learn that. So this is why it has to be this, or maybe this is why that doesn't work. Okay, so a couple of things to note here. First of all, the hardness here did not come from having a complicated reconstruct. Like the forward model is very simple. It's actually just linear in-painting problem, right? So that is not where the hardness comes from. Their prior is quite complicated. Maybe that is where it comes from. But I think one of the reasons it's hard is I don't think that it's actually so pathological. So here, what I have here is a cartoon version of this instance, which I think has the same. I don't think there's a proof for this, but it has the same kind of hardness issues, and yeah. Okay. So that's what I'm going to do. Basically I'm hoping that the takeaway is that that posterior sampling hardness is not very pathological. It is that instance is pathological because they had to prove it, and because right now we're not going to prove anything, this instance is quite simple. Okay, so it's the same kind of instance as before. My prior is supported on these. My prior is supported on these like vertical blue bars.
A two-dimensional space.
Yeah, it's two-dimensional. My prior is the blue stuff, and then the measurement that I get is this red line that goes through, right? And each of these bars, right, it has some gaps in it. Each of these bars has some gaps in it. So the actual posterior is just mostly on these two bars here. So it's on these two, and then sorry, on this one as well. It misses these ones in the middle, right? Now the problem is that at high noise levels for the prior, you don't notice this, right? I don't have a picture. Okay, at high noise levels, what will happen is that you'll kind of, these guys will all just.
High noise levels for the fire, what does that mean?
So if you look at, so in your algorithm, which requires scores, right, at various noise levels, if you use high noise level scores in trying to solve your posterior sampling problem.
If post prior is convolved with the Gaussian with a large variance, so it's much less than prior.
Yeah, but
Right.
John, I always have that. I'm learning the score at every
Yeah.
different thing.
So what he has shown there is P0, that original picture of
P0. Okay,
P0.
you're saying like the critical structure of P0 is destroyed very early on.
Yes, so the part of P0 that tells you which of these modes is consistent with your likelihood is quickly destroyed by the noising process. This is the same thing that happened in the lower bound instance. You had these like different combs, and then quickly when you noised them, they became the same, and you could no longer tell which of the modes is like consistent with your measurement and which is not, because you quickly noised it and it's gone now. So at high noise levels, you genuinely don't know. You never know. Like once you start to noise this, I don't know which of these modes, the vertical, like
Particularly be any one of these five.
yeah, any of the 5 modes, right? We don't know this. Now, at low noise levels, you do know. By the time you get to a low noise level in your, imagine a DDPM-esque algorithm, right, where you go from high to low noise. By the time you get to a low noise level and you realize that your mode is missing this in between, like, is missing this part, right? You've kind of committed to a mode, right, in your sampling process. Now, I think the reason this isn't a proof is because there's nothing to prevent you from going back out, going to a, right? But roughly, the philosophy of DDPM is that you use the high noise level scores to get this really fast mixing thing, right? So, Langevin would take forever to mix on this kind of a distribution because there's so many disconnected things. But because we're running, the benefit of DDPM is that at the very start, the most noisy iterate is actually independent of where you'll end up at the end. And so you could start anywhere, and because of you have these high noise level scores, it jumps around very well.
Clarify your saying. It's not about independent, it's independent of the prior. DDPM originally starts with pure measurements. That's what you mean to say, not independent of where you end up.
What measurements?
Right? I mean, posterior, DDPM at very, very high noise levels, you don't care what include priors. That's what you mean.
Yeah, right. And this is why DDPM, this is the mechanism, I think, with which DDPM samples so well, is because you're very uncommitted at high noise levels to a specific mode in the distribution you're trying to sample from. This is something Langevin does not have. This is a property that, and actually that's something, this is the first thing we'll talk about on Tuesday, is Langevin, once it gets to a mode, very quickly it'll find a mode and then stick with it forever. And this is why when you have like a mixture of Gaussians, the mixing time issue of Langevin comes from actually jumping from one mode to another, not in finding a mode in the first place. The novelty of the high noise levels is that it allows you at the start of your algorithm to move around very freely in the space, and so you can get kind of anywhere. But the problem is, when you're doing posterior sampling, you don't want to get anywhere. You want to go to a specific mode, and the information of which mode you want to go to is just not there at high noise levels. Like if you imagine a different prior in which, let's say this bar was complete, versus it's not, like whereas it has a gap, the scores at high noise level are basically identical. So you wouldn't be able to tell that this is If you just use high noise level scores, you would never be able to tell that. You need to come down to a low noise level, and then the low noise level, all you really know is that, oh, this one didn't work. It doesn't tell you anything about which one would work. And so when you have this kind of thing where you need to get down to a low noise level to know whether your sampler worked for this likelihood or not, then posterior sampling is hard to do. This is what they tried to formalize, and but it's actually a much simpler problem, I think, than that. Like this is really what's going on.
When you're saying DPM, we're always talking about like DPS-like thing where I have
Yeah.
additional grad log py given x plus grad log px.
Not really. Okay, I'm talking about kind of a vague abstract algorithm that does posterior sampling by going from high noise level to low noise level. I don't really have an algorithm in mind.
Because DDPM versus something else, we're not even talking about an algorithm. We're just talking about this reverse process, which is guaranteed to sample from Px, and you're somehow giving an idea of why that's hard.
Yeah. Okay. Right. So because I don't have a specific, yeah, this is really just the idea of why this might not work. Going from a high noise level to a low noise level, this type of algorithm. The reason it's difficult to make it work is this. I'm not saying which specific algorithm. I'm not talking about a specific algorithm, but this is just a cartoon. I just wanted to give some intuition for why this is so.
This is useful because the other view is just that I have a problem that's hard to invert. Any puzzle, I have a Sudoku problem that is the posterior sampling equals solving that problem. So it's easy to believe that posterior sampling is hard. It's as hard as solving any hard problem.
Right. But I think it's actually much harder than that. So I think it is even hard to do simpler problems using standard algorithms. So if you want to actually prove a lower bound, obviously you have to be much more robust. But I don't think that their result is true for like hard problems like this Sudoku or something like that. But I think this is just true. Even for simpler problems, it's really hard to get posterior sampling to work well. This is a very simple, even this picture to actually to find an algorithm that actually correctly samples from the posterior, even for this, I think is not very easy. Things like DPS, for example, fail.
I want to understand this picture. I still don't understand this. So at high noise level, this picture would be, there is no blue bars at all. They're just a Gaussian center. What would the picture look like?
Yeah, so at very high noise levels, you're right. It'll just be like that. Because the dotted line would still be, okay. The dotted line would be somewhere like this. So at high noise levels, it's just Gaussian. But at not so high noise levels, but still relatively higher noise levels, what happens is you get this thing where all of the little gaps go away. I don't know where the gaps are, but you see the modes. And so a reasonable sampler will just go and sit on one of these nodes. And you don't know which one you should go to. You just go sit on one of them. And then as you denoise more, again, vaguely, I don't want to commit to an algorithm.
Continue.
Right. As you get to lower noise levels, you will realize that you'll start to recover this kind of structure, and your sampler will not allow the prior scores won't allow you to go from here to here with your sampler because the score will oppose it very strongly. There is no mass there. But at that point, you have you cannot. It's very hard to get an algorithm that goes from here to there, that realizes, oh, this is not working. Let's go to a completely different mode, and then just jumps to a different mode and starts to solve the problem there. This is the thing that's hard to do. This is where this certificate type of hardness comes from. Once I'm in the mode, it's easy to know that this is not the right mode. But it's actually hard to know which is the right mode to go to, and it could genuinely be hard to find that out. And so, right. So that's the thing.
So does this hardness require exponentially large number of modes? And that's where it's good. So if you have, for concreteness, let's do the algorithm is a backtracking algorithm. Once you commit some mode, it can only search within the mode. And if it doesn't find anything, it restarts the problem.
Yeah.
Then such an algorithm will take, we are not anyway proving any lower bound, just for inclusion.
Yeah.
Then you restart this problem. At the high noise level, you have a standard Gaussian. find something, as you collapse, you will commit to some mode at random.
Yes.
Because you can't distinguish any of the modes at low until you get to low noise level.
Yes.
And with high probability, you'll be in the wrong mode.
Yes.
That's roughly why it's exponential.
Yes. In fact, you can't even get a slightly higher probability of coming to the right mode because that would be equivalent to inverting a one-way function. It's like you literally will just end up with a uniform distribution, and that's kind of the best that you can do. So the paper is in much more detail about this, and there's a strong version of the one-way function hypothesis which says that there exist one-way functions that are exponentially hard to invert, and then they have just an exponential lower bound for posterior sampling, which basically just comes down to saying the best that you can do is rejection sampling, and you can't do anything better than that. Right.
I see. And that basically means that is easy to show it's exponentially hard because you have to sample forever before you can get it.
Exactly.
It's what your example from last time was clear. Yeah, I want to find a picture of a dog. So I'll sample a picture. It's not a dog. Try again. It's not a dog. And
Yeah,
go on doing
it is.
for all
It's
boxes.
actually shockingly hard to do better. I spent a lot of time trying to do better than this, and it's really hard to get like provable posterior sampling without. So one way to avoid all this is to make like really strong distributional assumptions on the prior and the measurement model and things like that. So if everything is Gaussian, for example, then I think you can do it. But even if your prior is a mixture of Gaussians, it starts to become hard to actually show anything.
Of course, the fact that it actually works means that.
Yeah, something else. Who knows, right? So yeah.
So tomorrow's next.
Okay,
class,
you could address this by finding distributional assumptions that make it work. But this is a pretty straightforward picture, and it seems like unless you literally say that everything's Gaussian or something like that, it's very hard to make it work.
So I want to add one thing. So there are two ways to try to make this work. One, you basically say that, and you said take strong distributional assumptions, or strong, weak, whatever you want, measurement assumptions, so that things apart. Option number two is
Yes,
maybe you
simplify
don't
the
care about
problem.
posterior sampling. You care about, so when we say that we want to posterior sample and find an image of a dog which is gold color. Okay, how do you know how many dogs are actually gold color in the universe of all dogs? You just want to find a dog which is gold color. So you measure. So one option is I just want to have a support to be correct, or I want it to, or some other variant of it, some other variant of posterior sampling which even finally has the same operational use. And that's really what he's going to talk about next time.
So we'll
the definition of posterior.
So where posterior, like if inverse problems were like the motivation to study this jump here, where we decided to like optimize this, minimize this expectation and put this KL penalty, we made that up. That was not part of like the inverse problem thing. And it's silly to do it in hindsight because this problem is hard to do, right? We already, this what the lower bound is saying is this is actually hard. So then why do this, right? Maybe there's a simpler
version of this is easier, and that's also a good enough approximation to the original MLE problem.
This is conceptual. This is not an algorithm.
No,
Writing that down is because we can agree that this is a reasonable thing to desire.
Right, but the algorithms that we made were trying to solve this problem.
Yeah.
Right. So I'm saying that's not necessary. Okay.
We are trying to find all distribution for a single Y. And it says this.
this is the connection between posterior sampling and the original optimization problem. There's a large enough community who thinks this is reasonable or have been working on this problem, whether it's reasonable or not. You're right. And it turns out that the optimal solution for this is hard in general. So we should step back and say, what is another reasonable version or unreasonable version, which again operationally does the same thing, which is sample, which is consistent with measurements and consistent with the prior in some soft manner. So that's going to be the next section.
Yeah.
That's basically the high level takeaway of all this.
Yeah. Actually, this is all I've got for today because the next part would be too big. We'll just talk about it on Tuesday.
Stop at.
Yeah.
Can you speak louder? Because people on mic don't hear anything.
Okay, so I have a question. Suppose like we had trained like an initial DDPM model which does all of this. And then after that, are you familiar with like reflow and things like that?
No.
Okay. Are you familiar with flow model?
Yeah.
So the idea behind reflow is like you train your flow model again except this time, instead of starting with the cross product as your coupling, you start off with your original sampler as your coupling. The
Okay.
idea is that your flows get straighter and straighter.
Okay, okay.
So if we suppose solve the reflow problem well, would you think that then posterior sampling would be easy because your current point is highly correlated to where you'll end up, so you'll be able to easily figure out which mode you're going to at the start, even at a like quote unquote high noise.
But these are not posterior, these are just generative models. All
Yeah,
your
but-
how do you do posterior sampling with that then?
No, but if you just want recovery, maybe.
The sampling is basically at the high, what he's saying is at the sort of medium noise level. You don't know if the point you're going to corresponds to being like satisfying your constraint or not. But if you had like a highly straight flow, at any noise level, you would know if you're satisfying your constraint or not. So if you solve that, if you manage to get very straight flows, which I don't know if that's a hard problem, but if you manage to get those very straight flows, would you be able to solve posterior?
So no, because this is a lower bound, right? Are you saying so? It is a low. This is a very general.
You might need different assumptions to be able to do.
No, I doubt it because what would it mean a flow model? The only noise is at the input. So you have to decide at time zero, you have to choose your input, you have to twist your input,
Yeah.
such that you get into the right path. And that will be the hard one. So in a flow model, it's a completely different setting. All the noise and the decision is made at one time, at time zero.
Yes.
Okay. So now you're saying, how do I tilt my random input sample?
Yes.
And that is not clear at all at that point. Fair. Okay. So I don't think what you're suggesting is going to help. The key, I think this picture is like, it's about distributions which at high noise level at the other end are indistinct. They're mull. You cannot figure out which mode you want to get to. I think that's the cleanest insight from all this stuff.
Yeah. But I'm wondering whether it's a question of whether you can't figure out where you can get to, which would be solvable through flow, or whether it's a question of the noise.
So I think it's pointless to look for an algorithm to fix it because it's provably hard. That's the really nice thing about the proof. That don't think about this problem.
No, but what I'm saying is if you go through the proof first and you try to look at reflow, what would happen is your reflow would be very non-smooth. Like the flows that you would get for that would be high and non-smooth.
I don't know whether that is true.
I will say that this lower bound is not for DDPM-esque model algorithms. It is just a lower bound. So unless you're
So there always the prior is the prior, whatever more sampling algorithm you have.
Yeah.
So anyway, let's stop the recording at this point. Thank you very much, Advait. We'll continue next time.